So something else we can use the derivative for is something known as L'Hopital's rule. In the 1690s, Johann Bernoulli, who was rated by Johann Bernoulli as one of the 5 greatest mathematicians in Europe, began teaching calculus to Guillaume de L'Hopital, a French nobleman whose nearsightedness disqualified him from military service. L'Hopital proved to be a good student and decided to write a textbook on calculus, the first ever written. He hired his old teacher as a consultant. In exchange for a rather considerable sum of money, Bernoulli agreed to answer questions presented by L'Hopital and, in modern terms, waived rights to his intellectual property. In the course of writing his book, L'Hopital came across a type of problem that had never been solved before and asked Bernoulli about it. Bernoulli solved the problem, L'Hopital published it in his book, and the method has ever since been known as L'Hopital's rule. And, while it was in fact discovered by Johann Bernoulli, it is in fact L'Hopital's rule, bought and paid for. So the problem that L'Hopital came across that Bernoulli solved is this one. And if you can't read French, here's the English version. Suppose f of x and g of x are continuous and differentiable in the neighborhood of x equals a, except possibly at x equals a itself, and both limits are 0. Then the limit of the quotient is the limit of the derivatives. And an analogous result holds for one-sided limits. Now it's very important to understand and remember that L'Hopital's rule only applies to limits of the indeterminate form 0 over 0, and L'Hopital's rule does not actually calculate a limit. Rather, it says that one limit is the same as another limit. Now, just a quick note, the circumflex often indicates an omitted S in medieval French. So, hôpital in modern French was actually spelled hospital in medieval French. And if you've listened to me this far, you know what to expect. Far too much wordplay around this connection. So let's take a simple initial example. Find the limit as x approaches 1 of log x over x minus 1. So even though the problem says to use L'Hopital's rule, let's go ahead and verify that we can use L'Hopital's rule. So the thing we have to check is to make sure that we have a limit of the indeterminate form 0 over 0. And we see that as x goes to 1, log x goes to 0, and x minus 1 also goes to 0, so this is something we can use L'Hopital's rule on. So we'll apply L'Hopital's rule, that's the derivative of log over the derivative of x minus 1. So we'll take the derivative of log, the derivative of x minus 1, which simplifies. And remember that L'Hopital's rule does not find a limit, we still have to find the limit. And we get a claimed limit of 1. But while we trust our results, we should verify them. And again, the claim is that if x is close to 1, then log x over x minus 1 should be close to 1. And so we'll try a value of x that's close to 1. How about 1.001? And our work suggests the limit is accurate. So what about the limit as x approaches 0 of x cubed over e to the x minus 1? Since x cubed and e to the x minus 1 are continuous and continuously differentiable at x equals 0, we can try to check into the L'Hopital. So we'll fill out the admissions paperwork by finding the limits of the numerator and denominator. And since they both go to 0, this is a L'Hopital's problem. So our limit as x goes to 0 of our quotient is the limit as x goes to 0 of the derivative of numerator over derivative of denominator. Again, remember that L'Hopital's rule does not actually find a limit, it just says that one limit is equal to a different limit. So we need to find the limit as x approaches 0 of 3x squared over e to the x minus 1. But this is still an indeterminate of the form 0 over 0, and so we should apply L'Hopital's rule once again. Of course, our insurance company might not pay for another night's stay, so we have to verify that we are allowed. So we'll take the limit of the numerator and denominator. And since both are 0, L'Hopital's rule can be applied once more. And we get a new limit. Now it's important to recognize that we still have to evaluate a limit at some point. And this time, as x goes to 0, 6x goes to 0, and e to the x goes to 1, and so this limit can be evaluated directly. Well, let's find another limit. So as x goes to 0, both numerator and denominator go to, which means we can be admitted to the L'Hopital, applying L'Hopital's rule. And this time, we get our discharge papers because e to the x doesn't have a limit of 0, so we can't stay at the L'Hopital any longer. So what can we do? The important thing to remember is that L'Hopital's rule only finds an equivalent limit, so all prior strategies for finding limits may be required. Since this limit can't be admitted to the L'Hopital, we'll have to evaluate this limit using some other method. And we might note that in this case, as x gets close to 0, e to the x gets close to 1, and 3x squared gets close to 0, but always stays a little bit more than 0. And so our limit tends to positive infinity. Well, let's support that answer numerically and see what happens. So we're looking at what happens to this expression as x gets close to 0. So we'll try out some x values that are close to 0 and see what our expression is. And since all of these x values are positive, we'll take a couple of negative x values and mix it up a little bit. And we see that this does make it appear that as x gets close to 0, our function values do get close to positive infinity.